Welcome to another live session for the online course. I think we're coming up on maybe our 50th. We've done this quite a few times. And I'm sure you've never asked the same question twice, and I'm sure I've never given the same answer twice. So the floor is open for your questions.
All right, the first question from one of our students that is live with us now asks, one of the last times we had one of these sessions, you spoke about a black hole at the center of the universe. Can you please provide a little bit more insight into how we know this to be true? What's it called and what are its characteristics?
So I hope I didn't say at the center of our universe, because there is no black hole at the center of our universe, because there is no identifiable center of our universe. The cosmic expansion happens uniformly in every direction and at every location. But I was probably talking about the black hole at the center of our galaxy, the Milky Way. And there is very persuasive evidence for a massive black hole, about 4 million times the mass of the sun. This evidence started accumulating in the 1980s, and it's just been building steadily to the point where, of all the black holes in the universe, most of which, of course, are dead stars, so they're black holes that are somewhere between 3 and 30 times the mass of the sun. This is the best evidence for any black hole of any mass. So it turns out that our best evidence for a black hole is actually a very massive one, about 28,000 light years away in the direction of the Sagittarius constellation. Now, if you look towards the center of the galaxy by eye, in visible light, if you just go out on a night where you can see the galactic center, better visible actually in the southern hemisphere, Sagittarius is a ragged region of dense stars and dusty clouds, and actually we cannot see the galactic center. The pathway to the center of our galaxy, 28,000 light years away, is so filled with gas and dust that it's like looking through a closed door. I think about 1 in a billion photons from the very center of our galaxy actually reach us. Now that's visible light photons. If you move into the far infrared or the mid-infrared, the situation becomes a lot better, because dust is not absorbed, deflected, or obscured by, it doesn't obscure, deflect, or absorb long wavelength radiation as opposed to visible light. So you can see the galactic center at infrared wavelengths. So in the 1980s, when we got our first large telescopes of 8 and 10 meters in size, and we got our first arrays of infrared detectors allowing us to image more than just a single pixel on the sky, people started looking at the center of our galaxy at 2 microns and 3 microns. Those are wavelengths that are roughly 4 or 5 times longer than visible light. And they saw stars, individual stars in motion, and applying Kepler's laws to their orbits, were able to deduce the mass of a dark object and show that it had to be a very condensed and collapsed object, not a star cluster. This evidence just got better and better over time as the observations improved, to the point where there's really little doubt that something like a massive black hole sits at the center of our galaxy. And it gets a lot of study now continuously as people try and look for stars that are going behind the event horizon. They try and refine measurements of the mass and actually try and make images of this black hole at millimeter wavelengths.
All right, the next question is from another student who's on with us live, who asks, is there any evidence for primordial black holes, and how could we observe such a small object in the future?
So that's an interesting question. Many theories of cosmology and the Big Bang do speculatively predict there would be primordial black holes. That is to say, black holes that are created very early in the cosmic expansion. Remember, the universe originally was exceptionally hot and dense, and the gravity was extremely strong. And so in models of the Big Bang, it is possible to generate a froth, a large number of very small black holes early on. Now, according to the Stephen Hawking idea of black hole evaporation, black holes that were generated with small masses, which is to say, much smaller than the Earth, much smaller than a human body, but literally microscopic or dust grain size, those black holes evaporate very quickly in a fraction of a second when they're subatomic size, and they would release a flash of radiation, so they could not persist. There's possible indications that the energy released from these evaporating primordial black holes might remain as an imprint, say, on the microwave background radiation. So people looking for these very early and very numerous and low mass black holes are looking essentially for their radiation imprint, because the black holes would have evaporated by now. There's a second type of primordial black hole that people are also actively searching for. And this is essentially from the era of the first collapsed objects in the universe. Remember that before there were stars, the universe was essentially made of hydrogen and helium. It was fairly hot and fairly dense. We're talking about a redshift of 20, which means the universe was roughly 20 times smaller and 20 cubed times denser, which is very dense. And the microwave radiation was 20 times hotter than it is now, about 60 Kelvin. Now, in that situation, models and simulations suggest that very massive clouds can collapse to form black holes that are very large, larger than the ones we typically see in our galaxy around us. That is, black holes up to 40, 50, 60, 70 times the mass of the sun. And these would become essentially the seeds for galaxy formation. And these black holes would persist to the present day. They would have subsequently merged to become even larger, perhaps turning into the giant black holes we see at the center of galaxies. So people are very interested in observationally testing the idea of this very early regime of structure formation, where black holes may have been amongst the most massive objects that formed early, because in the models of star collapse, you actually form very massive stars early on, more massive than we see in the local universe.
All right, the next question is, since we haven't technically seen a black hole, is there a possibility that they're very different than we think? For example, that they don't have infinite density and are spewing out matter, causing a massive explosion or something like that?
Absolutely. Our information about black holes is very rudimentary, so that's always worth bearing in mind. So black holes were predicted out of the theory of general relativity, and it's notable that Einstein himself simply didn't believe that black holes were real. He thought they were, in the 1910s and 20s, he essentially thought they were artifacts of his theory and not real. He actually thought the same thing about gravitational waves, and of course, first detection of those happened less than a year ago. So there was a widespread skepticism, not just with Einstein, about black holes not being real. So it took a long time, observations through the 70s and 80s on binary stars, where one of the companions was in a Kepler orbit, was clearly massive enough and dead, so it had to be a black hole. And in fact, these black holes are not dark, because the companionship of a normal star means the black hole can pull material onto it and emit a lot of radiation, and that's X-rays, and that's how we found these black hole candidates. So the evidence has improved, but as for our understanding of their properties, it's very simplistic. In the black holes have no hair idea paradigm from the 1970s and 80s, that just means that black holes are extremely simple objects characterized essentially by two numbers: one, the mass, and two, the angular momentum, because they form from stars that were spinning moderately slowly, and conservation of angular momentum suggests that the collapsed remnants of such stars, black holes, should spin very rapidly. So black holes have these two properties, and that's essentially all. So they have a mass, and then they have an event horizon size, which just defines the region from which light cannot escape and no information can escape. And that's really all we know from the theory, and we don't know more than that from observation. The question of whether black holes do have singularities, which is to say infinities of mass and density at their centers, is completely open, and it's a prediction of the theory, but it's also a problematic prediction, because any theory that predicts an infinite physical quantity has got a problem. And we know our theory of gravity is incomplete, and we know that at some level it doesn't work completely for black holes too. So the observational handle on black holes is very rudimentary. We've measured masses for a number of them, and we've measured indirectly with clever observations the spin of some of them, and those are the two basic properties, and that's about it. The Event Horizon Telescope, a radio interferometer that's starting to take data now, and we run part of that project out of Arizona, it's going to try and attempt to measure the shadowing of a black hole event horizon in the center of our galaxy, that massive black hole. And that may lead to the measurement of general relativistic effects from the black hole, but it actually won't measure the interior properties inside the event horizon. So I would say the theory of black holes is still under development. The observational approach on anything other than their mass and spin is in a very early and rudimentary stage. And the observations are difficult enough that that actually isn't going to change very quickly.
All right, the next question is from someone who is on with us live, who asks, what are the chances to build a colony on Mars?
So Elon Musk has recently gone public with a visionary idea of a century from now, potentially a million humans living on Mars in self-sustaining colonies. Getting to that point, even in 100 years, is an extraordinary challenge. Most people put the price tag on setting up a minimal Martian colony. That would be a colony of really just half a dozen, maybe a dozen people, with resupply from the Earth, so not fully self-sufficient. Most people put that price tag at something like $50 to $100 billion. That's a lot of money, and they put the time scale on that minimal colony to be 15 to 20 years. NASA's program would not get astronauts there before 15 years from now, and even Elon Musk admits that that's roughly the time frame. That's a lot of money. It's, of course, half of what the space station cost up to this point. So we have spent similar amounts of money on challenging projects in space. And the private sector can probably get that kind of money together. Elon Musk himself is not good for it, nor even is Jeff Bezos, the head of Blue Origins, who also will develop a rocket that can get to Mars. But these billionaires are able to harness resources that could probably get up to that amount of money over a few decades. So that minimal Mars colony, I do think, will happen within, say, 20 years. But making it fully self-sustaining and independent of the Earth, that's quite a challenge, because that means everything has to be generated locally. The Martian arid soil is good for getting oxygen and extracting some water. Everything else would have to be grown. All the nutrients, medicines, all the things that humans need would either have to be imported very expensively or in some measure created, manufactured, or grown on Mars, which would take a lot of infrastructure. So I think the self-sustaining Mars colony, beyond some minimal number of people that spend a few years and are replaced by new people from the Earth in a permanent habitat, but with a rotating set of people, I think the permanent colony, we're probably talking 30 or 40 years. And it would be a small one, nothing like Elon Musk's million people.
All right, Carson, who is on with us live, has a question about space travel and is interested in all of the ring-shaped spacecraft that spin for artificial gravity. How do you get them accelerating that way? And would it be more stable to make multiple counter-rotating rings?
Yes, good, very good question. And indeed, the space artists have been drawing space wheels, rings, space colonies for decades, actually, back since the 60s and 70s. And that's a sort of artistic rendition of the ring. But as the questioner implies smartly, when engineers come up with such a design, they are aware that angular momentum has to be conserved, and it's very energy expensive to spin up a huge, massive object, because these would be massive objects and enormous objects up to some significant speed, significant enough to create a fraction of Earth gravity. So yes, all the space ring concepts that engineers have had a hand in do involve embedded counter-rotating rings, so that net angular momentum is zero. And solar energy typically is used to gradually spin these things up, and it would take a while. I mean, it could take months or a year or more to fully spin up a large wheel that was a habitat for, say, a few hundred people. Now, these are just designs. These wheels that would be, of course, constructed in Earth orbit. So you'd have to get the materials up into Earth orbit and then assemble them in orbit. So it's a modular design. The cost of doing that with present-day space program is unattainable. I mean, these kind of wheels are not going to be created in the next couple of decades. But people are still working on the idea of habitats. The furthest the game has got is Robert Bigelow, who is I think he's a billionaire. He's the head of the Motel 8 company, and he has had significant NASA contracts to put inflatable bubble habitats and attach them to the space station. And these are precursors to what he plans will be hotels in Earth orbit, zero gravity hotels as a commercial proposition. So that's the closest any private entity or NASA has come to a sort of habitat in Earth orbit, and they're quite modest, like a size of maybe a small family home for the biggest of them. They're quite modest compared to these visionary space wheels. Those are a long way off.
Right. The next question is, if terraforming was found to be feasible on a planet, how many years should we wait after the planet gets suitable for human life to settle there?
So terraforming is possible in principle. I mean, there are no laws of physics that prevent it. There's no fundamental obstacles. It's a lot of engineering. It's a lot of very expensive engineering. And NASA has actually been studying this, in a sort of visionary feasibility sense for decades. I think the first Martian terraforming design study dates back to the 1970s. It's very hard to put a price tag on it, of course, or a time scale. But fully terraforming Mars, a small world, significantly smaller than the Earth, but that's really the only one available to us to make habitable, because we know it's near the edge of habitability now, is in minimum terms a 1,000-year, multi-trillion-dollar proposition. Those are the numbers attached to terraforming Mars. And it's a multi-stage process where, to get to the point where humans, who presumably are already living there in sealed habitats, can actually venture outside and breathe the air, is literally centuries. Because first you have to raise the temperature of Mars to the point where liquid water can exist, and that's one of the hardest things to do. That uses a lot of energy to release that much carbon dioxide and create a greenhouse, sort of slow runaway greenhouse effect that feeds on itself. The second stage is to seed the surface with a biosphere of some kind, and you'd start with extremophiles. You start with organisms that can handle what would still be high level of radiation, would still be a fairly arid and cold environment. We have such microbes, we know they exist, and we'll use those microbes will gradually be used to thicken the atmosphere to generate oxygen. If it's going to be Earth-like breathable, it also needs a buffer gas. 4 out of 5 molecules in the Earth's atmosphere are nitrogen, and that's important metabolically for life on Earth, and again as a buffer against oxygen, which is of course highly reactive, combustible, and corrosive as a gas on its own. Pure oxygen is a toxic atmosphere. So generating the buffer gas is not trivial either, and generating 1 part in 5 oxygen, or even close to that, is also a process that'll take centuries. So we know how to do it in principle. I'm sure the engineering is not very advanced because Mars still has surprises. We don't know enough of the Martian geology to know how this would proceed. But we know how to do it, and it could possibly happen in the far future.
All right, the next question is, how far are we from building a warp engine?
So warp drive is a favorite trope of science fiction in books and TV and film, most famously Star Trek, of course. And it's a nice vehicle in science fiction for getting around the galaxy and dealing with the vast distances between stars. Remember, the nearest star, Proxima Centauri system, is over 4 light years away. So a round trip to the nearest star is a decade. And so, humans are going to live and die in the time it takes to get beyond the next handful of nearest stars. So for exploring beyond our immediate environment of the next nearest stars, we need something that is at least approaching light speed, if not exceeding light speed. So there's 2 issues here. First, the warp drive itself, which is faster than light travel, essentially almost instantaneously moving you around the galaxy. That currently is against the laws of physics as we understand them. And there's really not any obvious loopholes left in that argument, to the point where most physicists, if you poll physicists, you would have 99% of them saying warp drive or faster than light travel of large objects is not possible. Now, there's a slight door left ajar in terms of quantum physics and quantum theory, because the concept of a tachyon, a faster than light subatomic particle, does exist in some theories of the fundamental nature of matter. It's not ruled out by observation. And so that's the door slightly open. But these are tiny subatomic particles, not big objects like spaceships. So faster than light travel, no. And then near light travel, which is what you would need to go beyond the nearest stars in a generation, say, that is possible. It's just enormously expensive in terms of energy. Special relativity increases the mass. As you increase the speed of an object towards the speed of light, the energy you're putting into propulsion, instead of increasing speed, starts to increase mass. That's part of the special relativity effect. And that means you're essentially, you're hurting yourself, because the more mass means more inertia, more resistance to a change in motion. And it's a situation of diminishing returns, which is why in special relativity and in standard physics, the speed of a continuously accelerating object asymptotically approaches the speed of light, which is to say never gets there. It gets closer and closer, more and more slowly, and never reaches it, for enormous cost of energy input. So even traveling near the speed of light, by near I mean within 20 or 30% of the speed of light, is fantastically expensive in energy. So projects like Breakthrough Starshot, which are trying to, in a visionary way, in the century ahead, try and accelerate tiny objects, nanobots, fractions of a gram, they're only trying to do it to about 5 or 10% of the speed of light. That's sort of the practical limit with current technologies of even accelerating a tiny little nanobot, let alone a large spacecraft. That we don't have the energy to do that at all.
All right, the next question is from email. What is the current status of the Kepler telescope and its most recent findings? And are there any follow-up experiments planned in the near future?
Sure, Kepler is not faded from the public eye, but after its massive release of exoplanets earlier this year, it sort of slowed down a bit. Basically, what we saw in the huge release of exoplanets that's taken the total now almost to 5,000 was the bulk of the Kepler mission. Now, Kepler was a fantastic success, and as it approached its sort of sunset period, when it was only supposed to, Kepler was only supposed to work for 5 years, and it pretty much matched its spec, and then it lost some of its position pointing capability. Since Kepler points at a very crowded area of the sky, this loss of Kepler's pointing capability really compromised its primary science goal. So Kepler, about a year and a half ago, moved to what's called the K2 mission, the second Kepler mission. Given that the detectors still work and they can take data, but without the pointing precision previously, Kepler has now moved to a type of science where it looks at larger regions of the sky than its initial survey, and tries to find planets in the same way by transits, given this larger positional uncertainty. And the K2 mission has been successful, so science is coming out of the K2 mission. The next mission, however, that's got people excited is a mission that was actually on a hard hold with NASA for a couple of years until Kepler proved so successful, is called TESS. TESS is the acronym, and I'm probably not going to remember what the acronym stands for right now. But TESS is a sort of complement to Kepler. The limitation of Kepler is that by staring at one region of sky very deep and finding all the exoplanets in that region of sky, these exoplanets and their target stars are very faint and far away. They're hundreds of light years away. And so they're very hard to follow up with ground-based telescopes. What we'd really like is a complement to Kepler, which does the same thing, looks for planets by their transits of their parent stars, but does so across the whole sky and looks for much brighter and more nearby targets. And TESS is that mission. So TESS is due to launch, I think, early in 2018. And TESS is very exciting because it won't necessarily eclipse Kepler in terms of the haul of exoplanets, just the body count. And that's okay, because the field has moved on. What we really want to do now is find the most Earth-like planets and learn more about them. And in particular, find the nearest ones that we can study with our big ground-based telescopes. So TESS is going to help us do that. And so it's a very important mission.
All right, the next question is from the live chat. Is there a chance that there are wavelengths with new characteristics other than the ones we find in the spectrum right now, longer or longer than radio, shorter than gamma?
Yeah, it's an interesting question. And the electromagnetic spectrum, in terms of physics, doesn't actually have a bound. It doesn't have a high bound or a low bound. Actually, I'll change that in a minute. it does have a high bound that's associated with quantum physics. But in general, the bounds on the electromagnetic spectrum in terms of radiation we can sense and detect are functions of our detection apparatus. They're not functions of nature's ability to create very short or very long wavelengths. So the current practical bounds on astronomy using electromagnetic radiation at the long wavelength or low energy radio end, the bounds are basically meter length radio waves, maybe 5 or 10 meter long. It's incredibly long wavelengths. Those are typically detected with sort of dipole antennas, radio telescopes. The reason why we can't go longer than that is not because waves longer than that couldn't exist or be produced in nature. It's because the Earth's ionosphere is opaque to a very long wavelength radio waves. They essentially bounce off the ionosphere. In fact, that's how we test the physics of the ionospheres, by bouncing long wavelength radio waves off it. So that means extraterrestrial radio waves from the universe can't get through the Earth's atmosphere. It's as opaque as the Earth's atmosphere is for X-rays or gamma rays. And we haven't actually had enough motivation to put a super long wavelength radio telescope in Earth orbit. It would be very expensive anyway. And so people are not clear that there's enough astrophysics in the very, very long wavelength radio waves for that to be interesting. So radio wavelength astronomy sort of stops at a few meters, but not the physics of electromagnetic radiation longer than that. At the short end, it's also based on detectors. So we use gamma ray detectors to detect very short waves. These are wavelengths smaller than an atom, getting down to a fraction of the Bohr radius of a hydrogen atom, say. And these, of course, do not penetrate the Earth's atmosphere. So all X-ray and gamma ray astronomy is done from Earth orbit. And gamma ray telescopes from NASA and other space agencies have been very successful at looking at the high energy universe in these waves. The limit there, again, is based on detectors, what kind of detectors we can create to look at even higher wavelengths or even higher energies or shorter wavelengths. If you actually want to go to the universe at even higher energies, what people tend to use is cosmic rays. So the tool becomes extremely high energy particles that are created in sort of natural cosmic accelerators in space rather than electromagnetic waves. And if you use those particles, you can get to energies that are trillions of times higher than even the highest energy gamma rays.
Next question is from the live chat. Is quantum teleportation possible? Is it true that some scientists were able to do it for a proton? If yes, what was the method and tools, and why is it not possible to do it for larger objects?
So quantum teleportation is possible in principle. That's actually a result that has a date attached to it. In 1995, a paper was written by Charles Bennett. I think he worked at one of the national labs, Livermore, I think, but I'm not totally sure. So it's a set of physicists writing pure theory, quantum theory, and they showed that the fundamental concern people had about quantum teleportation is not actually valid. And that concern was that it's called the collapsing of the wave function. The fact that when you observe an object, it's quantum probabilities that are sort of distributed in the sense that you don't know exactly where the object is or what its momentum is or what its energy is. Those would collapse, and so you'd be unable to transmit this information across a distance instantaneously. They showed that the wave function doesn't collapse, and work since then, in the intervening 20 years, has focused on what we call quantum entanglement. So the method that people are using to do the very first rudiments of quantum teleportation involve making split photon states or quantum states where the information is entangled, which is to say information about the state of a particle is coupled by this entanglement process to the state of a particle at a remote location. And the reading of that information between the two locations amounts to transmitting quantum information instantaneously. There's no speed of delivery of this. It's not been measured. If there is one, it's not the speed of light, apparently. And that's, of course, why quantum entanglement is such an intriguing phenomenon, because the dispersed quantum state information appears to be held simultaneously at distant locations, which seems to violate special relativity. So quantum entanglement is a phenomenon that's been measured, and over time people have taken those experiments from meter length scales in the lab, and I think the record now is intercontinental scales between labs that are on different parts of the Earth. So quantum entanglement, which is to say the instantaneous transmission of quantum information, has been shown across distances of thousands of kilometers. That's very interesting. However, it's only been done for single particles. And in the lab, on smaller scales, it's been done for basically handfuls of particles, a dozen atoms or maybe 100 atoms, I think is the most. So either the experiment has neither been done over large scales, like within the solar system or between stars. We wouldn't actually know how to do that experiment without going to the stars. And it hasn't been done with anything like the number of atoms in a real object. Forget about a human, which is a prodigious number of atoms, but even something like a ping pong ball or even a grain of sand, has trillions and trillions of atoms. So quantum teleportation is allowed in principle by the laws of physics, but it's going to be an extraordinarily difficult technology to develop.
All right, the next question from the live chat is, are white holes as real as black holes? If not, why? Shouldn't physics be symmetrical?
To take the last part of the question first, because it's important, yes, physics is supposed to be symmetrical. Symmetry is a foundational principle in physics. It's actually a mathematical principle. The symmetry of, say, particle physics, the reversibility of particle interactions forward and backward in time, the charge that is equal, whether it's a positive or negative charge, the symmetry between matter and antimatter, all of these symmetries are manifested at a quantum level in the mathematics of quantum theory. So yes, physics is supposed to be symmetric, but when it comes to black holes, the symmetry doesn't have to manifest to the size of a macroscopic object. So in principle, a black hole is a rupture in space-time or a part of space-time in our universe that's sealed off from us, that is inaccessible to us. And the concept of a white hole is the possibility that that place from which nothing can escape, that pinches off space-time and we see as a black hole, is potentially connecting to another part of the universe where that information can escape and does emerge, or energy can radiate, and that's a white hole. So the idea of paired black holes and white holes comes up, where they're essentially tunnel points in space-time between quite disparate space-time intervals in the universe. So the white hole concept exists in gravity theory, it exists in physics, but it's not a very well-developed theory, and there's certainly no evidence that white holes exist in nature. And it's not necessarily obvious that they should exist, because the space-time we occupy, our universe, is rather uninteresting topologically, which is to say it's almost perfectly smooth and flat space-time for the most part. And so, except for the very rare strange objects called black holes, where a little piece of that space-time is pinched off, there's no indication that our universe is convoluted enough that there could be places where you can go disappear in one part of space-time and emerge in another part.
Right, there are two questions from the live chat that are related. So the first one is, what is the most important thing you think the James Webb Telescope will help us study, solve, or see?
So this James Webb Space Telescope, by its original scientific plan and design, it's a sort of the longer wavelength version of the Hubble Space Telescope. It's a bigger telescope, 6.5 meters compared to 2.2 meters. It shifts towards the near infrared rather than the visible region. And so James Webb's fundamental goal was to detect what they call first light in the universe. First light being the era of the very first stars and galaxies, which we think occurred within a couple of 100 million years after the Big Bang. So in terms of a universe that's 13.7 billion years old, that's first couple of percent of the age of the universe. So looking for that radiation, which is obviously going to be very dim and highly redshifted, which is why you use an infrared telescope, is what the James Webb was really built for. Subsequent interest, of course, has come from exoplanets. James Webb was conceived before exoplanets were even discovered. And now that exoplanets are really hot and of great importance and interest, people have started to realize that James Webb will probably be used a significant fraction of its time, maybe a quarter to a third, to study the atmospheres of exoplanets and try and look for traces of atmospheric gases, something that's extremely hard to do currently. So those are the two main goals the James Webb will have.
Right, and then the next question is about the James Webb Space Telescope. Is it ever going to be deployed? It's already several years behind schedule already.
Yeah, it's been multiply delayed. Its current launch date looks like October 2018. It has, of course, like most NASA missions and telescopes, launch windows, and they're fairly common. They're not as widely spaced as the couple of year launch windows for a Mars mission. Almost certainly James Webb will go then, because it's so far along that there's no showstoppers remaining, which is to say all the major instruments have been delivered. They've passed their thermal vacuum tests. What happens is each of the major instruments goes to a NASA facility, a huge evacuated tank, which can simulate the space environment, including the radiation, and also including all the shaking that happens when it's launched. And these instruments have passed those tests. The next stage is integration of the instruments and the other parts of the telescope with the mirror into the infrastructure that will be launched. And that's happening right now. So it's very far along. The launch vehicle exists and has been successful the last few times it was used. So there's not many showstoppers. Also, James Webb has spent most of its money in development. Price tag is over $8 billion. It was originally, I think it was originally about $500 million. So it's way, way over budget, and it's way behind schedule. But it's going to happen at this point. It doesn't look like there are any more delays.
All right, the next question is particle accelerators in space, yes or no? Why or why not?
Yes, but they're natural, not man-made. The particle accelerators in space are so much better than anything we could do on Earth that for now, for the near and foreseeable future, astronomers will just enjoy the particle accelerators that nature has created. So basically, cosmic rays, we know of the existence of very high energy subatomic particles, usually protons, but sometimes slightly heavier nuclei, that are accelerated to 99.7 or 8/9% of the speed of light. Fantastic, prodigious energies. These are situations where a proton has as much energy as a well-thrown fastball. Extraordinary energy in a subatomic particle. And this is way beyond, factors of billions beyond what any ground-based accelerator could do. So particle accelerators in space, yes, we use them, we study them all the time. They're called cosmic rays. We try and understand how they're accelerated and how far they've traveled to get to the Earth. Building a human, sort of human technology particle accelerator in space is not really necessary. The only advantage of the space environment for high energy physics is, of course, the vacuum, the natural vacuum. But high energy physicists are able to create rings, storage rings, or even the LIGO experiment is another example. It's not quite as good a vacuum as like CERN's Large Hadron Collider. And these storage rings at the LHC have 10 to the -9 factor of 1 billion times vacuum compared to the air you're breathing. Actually more than that now, the best ones. So we can create such good vacuums on Earth over a large physical situation, a ring that's 10 or 15 miles in diameter, that there's no reason to do that in space. Even though the vacuum would be better, the cost of creating the accelerator in space would be prohibitive.
Right, the next question is from the live chat is, based on the actual development of technology, just 100 years ago, the airplane was invented. Where can you see aerospace technology in 100 years from now?
Yeah, it's a good question. It's very hard to predict. So the airplane was invented roughly 100 years ago, and commercial aviation sort of took off in the 1930s, and then boomed after the Second War. So it took roughly 2 or 3 decades to go from the very first airplane to commercial aviation of the first kind, where it was only very rich people that could afford to do it, and it was very uncomfortable, and most people didn't want to do it. And another 30 years into the mid-60s for it to become available to the masses. And then another 30 years to the 90s when everyone could do it, and I guess cheap. So that's the progression of air travel. If you took space travel as the next frontier, you might argue for that or even a faster time scale. And that would say that our first space program, and now I mean, of course, commercial space. Obviously, the space program dates from just after the Second War, the intercontinental ballistic missiles of the 1950s, turning into the Mercury astronaut program of the 1960s. We say commercial space really just started a few years ago. Then in 20 years, maybe we're looking at sort of mass commercial space travel in the near Earth environment. And then 30 years after that, perhaps we're looking at the cost coming down to the point where lots and lots of people are doing it, and the visionary or the rich people doing it will be willing to go to other places like Mars, or perhaps in the outer solar system to Europa to see the rings of Saturn up close and so on. So that's how I might imagine these activities going. So our spread into space, if it mirrors the progression of the aviation industry, does suggest some pretty dramatic growth in the next few decades.
All right, the next question is from email. My question is, recently reported was that the observable universe has at least 10 times more galaxies than previously thought. How is this affecting the calculations about the amount of dark energy and dark matter? Does this fact affect inflation theory also?
Yeah, so this story got some media attention. To astronomers, it's neither surprising nor actually that profound. It was a better census of galaxies done with the Hubble Space Telescope, but really the part of the picture that was being filled in by these very deep observations was the low mass end of the galaxy spectrum. So there are when we talk about galaxies in the universe, we should recognize that in any volume of space, like the one that includes the Milky Way, there are always far more dwarf or small galaxies than large galaxies. For instance, in our local volume, there's the Milky Way and Andromeda, two medium-sized spiral galaxies. There's the Magellanic Clouds, two dwarf galaxies, and then there's a couple of dozen really quite puny dwarfs. So there's basically 10 or 20 times as many dwarf galaxies as big galaxies. That's just a rough number, but the factor is large. And so you can see that in any census of galaxies, the number you get when you're just counting galaxies will depend very much on how faint you can go. If you go down to all and include all the dwarfs, you could easily get a factor of 10 more galaxies. And without getting into the details of the work, because there's a little more to it than this, that's what this work did. It was able to do the full census of galaxies down to smaller, more dwarf-like galaxies, which are important because they are the most dominant population. So it's a correct census, but because it's looking at dwarf galaxies, it doesn't really skew or change any of those underlying numbers about the universe. To go back to the local example, the mass of either visible or dark matter in the Milky Way plus Andromeda, put those two together, far exceeds the mass, the visible or the dark matter mass of the sum of all those few dozen dwarfs. So adding those dwarfs, counting them, increases the census a lot, but adding them to the amount of dark matter or visible matter, baryonic matter, doesn't change the total very much. And so that's why this work didn't really affect some of those cosmic numbers. And it had nothing to say about dark energy, which is really diagnosed in a completely different way.
All right, back to questions from the live chat. Where does the ekpyrotic model of the universe stand among other cosmological theories?
So the ekpyrotic model of the universe was designed to solve sort of dissatisfaction that people have with the standard hot Big Bang theory. In particular, the Big Bang theory is mute to the cause of the Big Bang. The origin, this strange quantum origin where everything, now we know these hundreds of galaxies, more than we thought a few months ago, emerged spontaneously, apparently from the vacuum, perhaps borrowed from vacuum energy, we don't know. The ekpyrotic model invokes higher dimensions, and you'll understand that string theory, or current sort of cutting edge theory of microscopic matter, always invokes dimensions beyond the 3 of space and 1 of time that we're familiar with. So the aperiodic model, out of a context of higher dimensions, which is part of string theory and so has become a part of the physics landscape, even though it's not proven, the aperiodic model postulates our universe as a sort of collision between three-dimensional surfaces or volumes within a larger dimensional subspace, or subspace within a larger dimensional overall space. And in that model, this process doesn't have to be the only one, and it doesn't have to be the beginning or the end of the underlying universe. So an aperiodic model, which is from the Greek for being born from fire, is talking about the Big Bang, but it's also saying the Big Bang isn't the beginning of everything, and that this context of higher dimensions allows you to spawn different universes, that come and go, that begin and end, and it's an endless process. So it's a way of explaining the Big Bang from a different physical context and proposing that the universe does not have a beginning to everything, but that the Big Bang is just the beginning of our local space-time behavior. And the evidence for this model, of course, the jury is out. Many people think that gravitational wave signatures are going to be the way we distinguish between this and standard Big Bang, just as gravitational waves are supposed to be the way we may demonstrate that inflation happened, if it did. So the jury is out on the aperiodic model.
All right, the next question, again from the live chat, is could space and time be quantized?
They very probably are, because the space-time continuum, that phrase itself comes out of relativity, omits the fundamental fact that we have these two irreconcilable theories of nature. We have general relativity, which speaks of smooth space-time as a continuum with curvature of space-time caused by mass energy density. And then we have the quantum theory, where nature is grainy, where everything is quantized. And these two theories are physically and mathematically irreconcilable. And so enormous effort has been put into trying to reconcile them. And essentially, it's at some level in physics community, it comes down to a philosophical distinction on whether you think the primacy of these two irreconcilable theories goes to general relativity or goes to quantum theory. I'd say the consensus of physicists, but not unanimous, is that quantum theory is more fundamental because it deals with the microscopic nature of matter. And in the quantum theory, it is indeed likely that space-time itself is fundamentally grainy and quantized. We just don't see that reflected in the theory of general relativity, which tells us that general relativity is not the final theory of gravity. So physicists are working very hard on coming up with a plausible quantized space-time theory that's fully reconciled with quantum theory and that is also consistent with general relativity, but makes new predictions that we can test.
All right, so we are basically out of time, but one of the people on the chat would like to know how a teenager like themselves could keep in contact with and interact with physicists for advice and help.
So obviously, I always want to encourage young people, teenagers, college kids to be taking interest in physics and astronomy and be able to pursue that interest. There are various chat groups you can join that are talking about physics or astronomy. There are obviously, wherever you happen to live, there is likely to be an amateur astronomy club or a physics club with the local university. Like in every major university I've ever been to, there's both a physics club and an astronomy club. They tend to give talks, they tend to do activities, they visit labs, they sometimes do experiments and scientific work, they publish, they sometimes even write papers. So use your local educational resources. You can go on Reddit, and there are Ask Me Anything forums that are run by physicists or cosmologists or astronomers. So the internet is a wild west, of course, and there's some pretty bad stuff out there. But as long as you look at the credentials of the people you're dealing with or talking to, then I think you can have some very good conversations with physics about physics or astronomy. Okay, that's our time for today. Thanks very much for participating. Great questions as always, and we'll be back in a week or so. Goodbye.